we, all right. So basically we want to know how can we better control this exposure, this bad health outcome? How can we mitigate or reduce the health impacts? So you see air pollution, we know again, air pollution has significant health impacts. We want to know what disease is associated with it. And we want to know how much is the impact, quantify the impact, and we want to know how can we better control it. To achieve all these things, so exposure is a central metric we need to rely on. So if you're not familiar, exposure is how much you're exposed to, individually, population-wide, how much air pollution is exposing people, like the quantitative metric. So if we want to do all these different things, exposure outcomes, quantify impact, design mitigation strategy, we need to get exposure right, because that's a number we need to rely on. So currently, now two of these major issues in getting exposure right is human movement and concentration distributions. The reason that is because if you think about what is exposure, because it's human getting contact with pollution. So if you have pollution in a remote island that no one lives there and nothing there, it's bare in the desert, no one cares, because what's the impact going to be? Nothing. Yes, you have pollution, but you have to have something that impact. So when you have pollution and human collocate together, that's where, when you have exposure, that's when you have a problem, right? That's where the impact will occur. So that involves two elements. The first element is human. The human has to be there. And then exposure concentration. So if we need to get exposure right, we need to first know the human location, then we need to the pollution concentration. But neither is easy. The reason I'm saying this is because first is human movement. We all change, or we all move all the time, right? We go home, eat, go to restaurant, go to movie, bunch of different things. We move, the individual location changes all the time. And concentration also changes all the time, not only spatially, but also temporally. It makes sense. Now, if you look at this figure right here, is now in the background, this grid is particle concentration is PM 2.5. I think everyone knows what PM 2.5 is. A teeny particle with the diameter, aerodynamic diameter of 2.5 micron or less. Now, the different color representing different hours. So the whole idea is, if you look at this individual, this is the individual, movement across one day. You see, it's the blue color is at night. This individual stays here. At daytime, this individual moves to here. Makes sense, right? Moves all the time. Now, if you look at the concentration difference, it's quite different, right? At here, it's a much lighter color. At here, it's much darker color, corresponding to very different concentration levels. Now, if we talk about exposures, right, then the first things we need to know, okay, if we want the exposure right, we need to know, again, two things, location and concentration. We need to get the location right. We need to get the concentration right, so we can better get a good estimate. If we do not have a good estimate, well, we cannot really accurately achieve all these goals, because exposure is a central metric here. Now, this is where my research comes in. My research agenda focuses on two things. First, individual locations, and then pollution concentrations. How do we get this better so we can get exposure right? So I'll start with the first theme, which is individual location. Now, in the past, now in air pollution health studies, say for example, if I'm an epidemiologist, I want to know, okay, if air pollution exposure give you certain health outcomes, what I would do is basically I recruit a bunch of people, I look at their exposures. But the problem is, let's say if you recruit 1,000 people, how do you get where they are? How do you characterize their movement? You can't. It's just very difficult. So usually what people do is they just assume, okay, this guy's going to stay here at the home location all the time. Or maybe just say, well, I'm going to assume 9 to 5, a 9 to 5 at work location, the other time at home location. We just make these assumptions because we do not have data. If I want to know where this individual is, I will combine with the detailed concentration information. That's perfect, but getting individual location is pretty difficult. Now, if you think about it, this is particularly problematic for some health issues. For example, if I'm interested in pregnancy outcomes, I want to know, okay, if exposure to air pollution give you a birth defect, for example, spina bifida, someone with the severe neurological disorders, I need to know, say, when this pregnant lady is exposed to the pollution where this lady is. I want to know the location so I can combine with concentration data, right? But the thing with some outcomes is, for the neurotube defects, it occurs in the first trimester. It means that, but the problem is that, in the first trimester, you're looking at something like, 6 months away or 10 months away. How to do that? I can't even remember where I was last week, right? So if we look at, okay, I need to know where you are 10 months away, no one can get it. It's just impossible. So, but how do we do that? Because if I'm interested in health outcomes with air pollution exposure, I need location data. How can I do that? So one part of my research is essentially use cell phone and smartphone data to better characterize human movement. Now, right now is, in the past 20 years or so, cell phone and smartphone has been, the market explosive growth, Now, I think almost universal coverage, almost everyone. I believe there's some recent data showing about 99% of the people, in the United States. I mean, even in developing countries, we're talking over 80% of people. They have either a cell phone or smartphone, right? Cell phone is basically something like even a Nokia 1110 black and white phone. A smartphone is something like iPhone or Android, right? So people have that phones. Now, the thing with the phone is that there are a tremendous amount of location information being continuously collected from these phones. Now, these phones continuously being collected and stored at different locations. Now, these location information can be very helpful for air pollution health studies. So we're going to briefly go over 3 of the different types of cell phone and smartphone location data, and we're going to look at their potential in air pollution health studies and how can we utilize this information to basically get a better exposure estimates to help us with air pollution health studies. Now I'm going to go, the 3 things we're going to go over is call detail record, Google Maps, and iPhone data. So we'll start with call detail record. Now, a thing with this is, again, as mentioned, in many air pollution health studies, we simply do not have the information of individual locations. So we just assume people stay there at their home, right? And we know it's not true because people move all the time. And again, to get historical data, let's see again, in the case of pregnancy outcome, if you want to get a pregnant lady's location data in 10 months prior, it's really difficult. It's just very, very difficult to get. But many people don't know that is that because near the universal coverage cell phones, if you have a cell phone, you have data, location data. Now, this particular location data is called call detail record, CDR. Now, the thing with CDR is that, okay, where it comes from is, say, you have a cell phone, you need to call, if let's say your cell phone needs to interact with the carrier, which is the Verizon AT&T, right? With the tower. If you make a phone call, if you make a text, if you want to maybe request some mobile data, your phone needs to connect to a tower. So when you do that connection, from a carrier side, they need to know, let's say, okay, who is making the call, right? For example, in the calling, who you're calling, at what time you're calling, right? For how long you're calling. And so this way, they can charge you, right? It's for billing purposes, they have to keep something like this. This is called call detail record. It has extensive information on your call, on your interaction, on your phone's interaction with the cell phone tower. This happens no matter you have a black white phone or a smartphone, because you have to connect to a tower. Now, when you do that in the engineering very back end of the carriers, they record this information. Now, a lot of times your exact location is not known because, unless they try in some criminal investigation, they can actively track you, right? But, most of the time they don't actively track you because why bother, right? But the thing is that they know the cell phone tower that handled your call. Makes sense, right? Because that's for billing purposes, you have to know that. And the cell phone tower are expensive, and the carrier, they know exactly where the cell phone tower is, and you cannot be too far away from the tower, because if you are too far away, you're going to be connecting to a different tower, right? So the signal is just going to be too weak. So you see what I'm saying? So the CDR, qualitative record, is something that the carrier has to keep for billing purposes, but it gives you a lot of information about where you are. Not exact, but you cannot be too far away. So on average, very roughly, so a cell phone connects to a cell phone tower about 100 times per day. So it's a lot. So for example, here is just one, you've seen this map before. This is one individual's call detail record CDR data. Now, if you think, okay, there are only a few circles, but it's much more than that, because these circles, over 300 circles overlap on each other. And they are the exact location, only happens at night. So you know what it means. It's this individual home. This individual home is not too far away from here. And if this individual's location, called CDR, occurs at daytime around this location, it's this individual's work location. So you can extract a lot of detailed information just by using the CDR data alone, like roughly where the home is, where the work is, a bunch of different things like that. So, and the good part is that because CDR is used for billing purposes, the carrier has to store it somewhere, and usually store it for a long time. They have to store it, right? So it goes back for a very, very long time. You can, if you think about it, if you want to know who you called about a year ago, if you don't change your phone, well, you know that, because you can look it up, right? Your phone will store the information, it's right there. So these are very important information. Now, what I want to do is, okay, now this is CDR data, right? So we know almost everybody has the data. It's a lot of information of an individual, but can we use it though, right? Can we use it in air pollution health studies? So what we did is basically we got our hands on a small, relatively small CDR database for Shenzhen, China, only for 1 day in 2013. So we want to know, okay, can we apply CDR data to characterize human movement for exposure to air pollution, and how can we do that? So what we did is, okay, we got this data in Shenzhen, China. Now this, if you don't know, Shenzhen, China is a close border of Hong Kong and in Guangdong province, and they have about 13 different monitors around this area. Now this is only 1 weekday in 2013, October. So it's a teeny data set, but even say by teeny, I mean, it have 35 million location record for over 310,000 individuals, still a lot. But, we're talking about a carrier that dealing with billions of location data every single day. So 35 million for 300,000 people is teeny, but still you can this give you an idea how massive the data set is. So what we did is, okay, you got this data set, and we track each individual along the way and combine with the location information with the concentration field estimated by this model called CMAP. If you're not familiar, it's fine. Basically, it's just air quality model give you the concentration field every hour at about 3 kilometer resolutions. So we pick 6 pollutants because we want to see if the exposure going to change, how the movement going to change. For the 6 different pollutant, PM 2.5, elemental carbon, which is black carbon, carbon monoxide, nitrogen dioxide, sulfur dioxide, and ozone. So we calculate 2 exposures. One we call it CDRE. You can think of it as dynamic exposure. We follow this individual along, combine with the background concentration, we get a good estimate of exposures. And then we assume, okay, this individual stay at home all the time, right? This is traditionally what's been done. We just assume, okay, this individual stay home all the time. We just only use the data at this home location. How do we know the home location? Here, the most frequent location at night. It's a very good estimate. So, and we further divided there is 300,000 people into 10 different groups with different movement levels, like based on how much they move spatially. And we just divide them into 10 groups and look at the difference of exposure among the 10 groups. Again, 2 exposures. CDR-based exposure, dynamic exposure, we track individual combined with location, with concentration. Home-based exposure, HBE, we just assume, okay, look, this is just, we just assume this individual stay home all the time. Now, if we look at the results, what we see here is that the x-axis is a home-based, which is a static exposure. A y-axis is CDR-based, which is dynamic exposure. Now, what we see is that you see different color represent different sample sizes. You see along the one-to-one line, there's so many. The vast majority of samples cluster around the one-to-one line. And if you look at regression, the R square is so big, it's close to 1, which means for the vast individuals, interestingly, if you look at their dynamic exposure versus static exposure, it's very similar. But you do see the very many vertical lines. These vertical lines meaning for these individuals, they have exactly the same home-based exposure, but their dynamic exposure based on CDR is quite different because same home exposure, very different CDR exposure, right? Makes sense because you can have 10,000 people live in the same community, but then they just move around. They move around differently, so their exposure is expected to be differently, right? And now, if we further look at their differences among different groups, we see that this is quite interesting because the pattern is very different. The first pattern is, I hope you could notice, is CONO2 and PM2.5. If you know that, they have a very significant contribution from traffic. So, the thing is that the biggest difference, this is the difference between the dynamic exposure and static exposure, and by 24 hours along the day. Now, you see around the afternoon rush hour, you start to see the big difference. Makes sense. Because if you think about it, most people, they work, right? So at daytime, 9 to 5, they go to a location, work, and around afternoon rush hour, they come back home, right? If you assume this person stays at home all the time versus, well, this individual stuck in traffic, of course, concentration is going to be different. So interestingly, we see the traffic pollutant, we see the biggest difference occurs at the afternoon rush hour. But it's not, the biggest difference is only found with people like group 6 with the 5 to 6, which is a moderate level of movement. Not those people who move around all the day time. Not those people who move around most, rather there's have people with a moderate level of movement. It's quite interesting. Now, SO2, let's ignore it because it's just too much, the difference too small. And another thing we see is ozone. Now, we see this is at afternoon 3 to 4 p.m., we see the biggest difference. And you see the direction is quite different. Now, this makes sense because, if you I assume many of you already learned about the ozone formation. So ozone concentration expected, ground level ozone concentration expected to be highest in afternoon, around 2 to 4 p.m. in the afternoon. So that's why you see the big difference around mid-afternoon, because this is where you have the highest concentration. Versus for traffic pollutant, the highest concentration you always find in the rush hour. Makes sense, right? Most of the time in rush hour. So, and also you see that the difference is that sign is different. Now this is negative, this is positive, right? Which means for traffic-related pollutant, if you assume people do not move, you're underestimating their exposure. For ozone, if you assume people do not move, you're overestimating exposure to ozone. You underestimate exposure to traffic, overestimate exposure to ozone. It's quite fascinating. That's just one example. See, what I'm trying to show is, look, it's a little bit complicated because it really depends on what pollutant you're looking at, right? Now, if we go a little bit further, okay, let's say, okay, for different pollutants, let's look at the exposure misclassification. Now, what's misclassification is that, okay, in approaching health studies, say, if I want to know exposure to something, give you, some increased risk of certain disease, what usually people do is they divide people into groups, right? So you already divide them into 4 groups, the different quartiles, and look at, for each group, you have different level exposures. Now, what this means is, okay, if you look at, this is group 2, group 6, group 10, a bigger group number means more movement, right? Now, On the left side is a dynamic explorer based on CDR. On the right side is home-based explorer, which is we just assume these people do not move. What I'm trying to show is here is that if you look, it was an increased movement. Group 10 represents the most, people move the most. You start to see that if you assume people do not move using HBE, you start to see that a lot of people was classified into the wrong groups. Because if you track people like where they are combined with concentration, it's better. But if you assume people don't move, you introduce more bias. And what I'm trying to say is, for example, here in quartile 3, only 38% of the individuals in quartile 3 was correctly classified by home-based exposure. 40% they're supposedly in quartile 3, but they were thrown into quartile 4. The remaining is thrown into quartile 2 and 1. Same thing in quartile 2, only 45% is correctly classified. 45% misclassified, that's thrown into a higher category. What this means is that, okay, if you do your epidemiology statistical analysis, but you are misclassifying like half the population in that group, you're going to have a big problem. This means that highly likely that you're gonna your results is not as good because a huge portion of people was thrown into a wrong group, and correctly classify people into different group is extremely important for statistical analysis. Makes sense? Now, the takeaway message here is, okay, first, I'm not saying, okay, everyone should move away from home-based exposure, which is let's just use the dynamic. You can't do this because let's say you're tracking 1 million people. How can you do that? It's impossible. Now if you look at here, which means the vast majority of people, they are still fine because their home exposure and dynamic exposure is just quite similar, right? So the whole idea is, okay, if you look at the population level, that the difference between dynamic static exposure isn't that big deal because it's just quite similar. And so traditionally, the traditional approach you use by assuming people stay at home all the time, it's fine. If you're talking about huge population level, but it is a problem if you look at individual level. The reason I'm saying this, okay, for example, if I'm interested in certain rare disease, like let's say again, birth defects, neural tube defects, it's kind of rare. It only happens on fraction, like thousands, only one in several thousand of babies. Now, if you look at individual level, you might want to try to track this individual as much as possible because if you look at this, at the individual level, you never know because you never know which group this person is, right? There's a higher chance this person is highly mobile, moves all the time. And if you do not track this individual movement, you never know where this person will end up with. Your sample population is small, you don't want to risk it. It's a better idea to better track this individual's location using cell phone data. And we also can see that if you do not do this, likely you underestimate exposure for traffic-related air pollutants in the afternoon, but you overestimate ozone exposure at mid-afternoon. So this can be problematic for health studies. All right, now that's CDR. That's one of the things, right? So one of the things, CDR can, it's near universal coverage, so everybody. But you see the problem is, everybody can clearly see the problem is, it's privacy. Because CDR contains so much digital footprint of near everybody, you can clearly see the potential is being abused. And as a matter of fact, starting from 2018, it's very difficult to get CDR data in the United States. The reason is because in 2018, you have a Supreme Court case with Carpenter versus United States. Now, this Carpenter guy is a thief. He's stealing things from several states in Washington, in that region. Now, how the cops track him down is the cops just look at CDR and found him, hey, look, this guy's CDR data always overlap with this serious incident where the stealing occurs. Of course, it's this guy, right? But then it gives the privacy concern because cops can access to anyone's CDR in the past. You see the problem, right? And so this case also went all the way to Supreme Court. In 2018, Supreme Court ruled that CDR data, core record, is private, which means you're gonna need a court order to be able to actually, you're gonna need a court order to be able to access CDR. This is the problem for me, because I need CDR for health studies, right? But you cannot do it anymore. I went to ATT. I was like, hey, I want my own data. Can you give me that? They're like, no, you're gonna give me court order. Some judge has to sign. Then, I can give it to you. I was like, how can you do this? It's just impossible unless you are involved in criminal case, right? So CDR is a big no-no now. In the past, it is okay, but now it's a big no-no. But then I'm still interested in how can we track individuals for health studies. So ideally, if I want to have the data like this, I want to easy to access. I like CDR is very difficult now and accurate. I want to be precise, accurate. I want to be a complete data set. Of course, I want in the case of CDR, you have 100 location data per day. It's pretty complete. You can get a good idea where you are in one day in a pretty complete thing. I want to know is good population coverage and historical availability. Population coverage makes sense because if I'm interested in health studies, I don't know who is going to have this health disease. I really don't know, especially if you're talking about rare disease, right? Also, historical availability. I want to be able to go back for a long time because it's really your disease outcome the exposure could occur for a long time ago, right? So easy to access, accurate, complete, good population coverage, good historical availability. I want something like this. Normally people would like to how it's impossible, but actually there are two options available, which, first thing I want to mention is Google Maps. And second thing is iPhone stick event location. Now, the first thing is Google Maps. Everybody uses Google things, right? You use Waze, Google Maps, of course, you use Google services. And especially Google Maps, it's the most popular map app on both iPhone and Android smartphones, which cover about 80% of the population nowadays. So the thing is that for many people, when you start Google Maps, when you turn it on, well, for the first time, Google Maps can ask you, hey, can I give you do you want to enable location history? Because it can give you better results, right? You'll be like, sure, why not? Many people just click, oh, okay, turn on, without knowing what's behind it. But in fact, when you click turn on location history, Google Maps will start collecting location data. Even say you're not using it, it's still collecting that once every few minutes in the background. So as long as you are signed in with your Google account, even say you switch phone, you switch from iPhone to Android phone, it doesn't matter. Google is collecting data, uploading it to its server, and which you can view your data. You can download the data very easily on Google's platform. If you're interested, you can just search Google Maps Google timeline, and you can see your data, like visualize your data where you have been. It tracks you all the time. The second thing is iPhone signal location. Now, iPhone is the most popular smartphone in the market in the United States, especially among younger populations. Now, in iPhone it has this feature called significant location. The idea is that when you have a new iPhone, you are very excited, right? And iPhone asks you, hey, do you want to turn on significant location? And you just say, sure, you click, and then start collecting your data in the background. And the data is buried deeply into your phone. And when I'm interested in this, okay, look, these are pretty potential good candidate for tracking historical human movement. But are they any good? No one have ever, I'm not saying no one, but I haven't seen anyone do iPhone data before. But Google Maps, there are some like very limited data information, but it shows it's pretty good. But how good it is? Can we use it? Any useful for appropriate health studies? So what I did is, okay, I carry the smartphone, factory reset everything only with Google Maps, and I carry the GPS logger with me for a week time period. So the GPS logger recorded my GPS coordinate every 10 seconds. And I'll let the Google Maps run in the background. And over the week, I want to see, okay, is it any good? So how good is the Google Maps data, right? Is it accurate? Is it complete? Now, this is just one intersection. So this is what when I was driving. So over the 1 week time period, you see this black dot GPS logger that clearly tracks the shape of the road because it's GPS logger, right? It records my GPS location. If you had got the Google Maps data, it's a little bit scattered. The reason is that on your phone, you cannot really, a lot of time you do not have very, very accurate GPS coordinates because that consumes power. So you already have an approximate location. You see it's noise. So when we see this, our first thought is, okay, is it any good? Can we use Google Maps data to do that? So what I did, okay, I cut into the entire area I was moving in a week into like different size grid cells. So I interpolate the data, the both GPS data, and also the Google Maps data, and then I count the time I spent in each grid cells. Now this is 100, 1,000 meter, a kilometer, 500 meter, 200 meter, and 100 meter. Now on the top is the daily. So basically every single day, every single grid cell. And this is on the bottom is weekly. So it's a weekly sum the time spent at each grid cell. So the whole idea is, okay, if you look at 1,000 meter, you see the correlation is really good. So which means is, let's say the root mean squared error 2.5 minutes. So which means Google Maps data can give me 2.5 down to 2.2 minutes level every single day where I spend my time. But the performance quickly degraded if you want to higher resolution. At the 100 meter, it's nearly unusable. So what does it mean tell you? Google Maps has issues. The biggest issue is accuracy. It's only, at 200 meter, it's barely usable. But 1,000 meter, it's pretty good, right? So what this means is two things. Now, if we go back to this here, it's pretty accurate to a certain level, of course. It's pretty complete because it captured all the grid cells I spent my time, almost all of the grid cells. It's easy to access. Now, if Google Maps data, it's very easy. All you need to do is just just search Google Takeout, sign in with your Google account. You can download it with a few clicks. Now, the next thing I want to ask is, how many people have it though, right? So if only, let's see, a handful of people have the data, it's not useful, right? So what I did a quick survey on Amazon Mechanical Turk. If you're not interested, so basically it's Amazon platform, you can take tasks, you got paid to do surveys. Now, this quick survey showed that, about 300 people showed that only about 60% of the people actually have Google Maps location data on their phone. 4% of the people doesn't have smartphone or Google Maps on the phone. 30% don't have the data, not sure, like 5%. So we're talking about potentially 60% population in the United States that have this Google Maps location data. It's huge. Remember, it's very easy to access. It's pretty accurate and pretty complete, right? So now, but the final question is how far back it's available though. So for me, it's my Google Maps data back in 2015 is where I started using Android. I was an Apple fanboy, before that, but I started transitioning to Android. I can see exactly day by day where my location is back to 2015. And there are various pilot scale in Europe shows that Google Maps can go back to over a year on average. And there are recent study in Washington show that Google Maps can go back to over 7 years. In my case, it's about 7 years, right? So you see the thing is, when I talk about something, Google Maps data that has a potentially huge population coverage, we're talking about 60% of the population have the data. It's pretty good, accurate to a certain level. It's pretty complete, a very decent, very good historical availability and population coverage. Now, it has good potentials, right? Makes sense. Now, the second thing I want to mention is iPhone data. Now, we mentioned iPhone has significant location, right? So I'm interested in this. So again, I carried iPhone 6s, which is which is old iPhone my wife is no longer use, so I just take it with me. And the GPS tracker with me for a month. Again, GPS tracks me every 10 seconds. At the end of a month, I just compare the GPS data with iPhone data. Similarly, I did a survey on Mechanical Turk, about 350 respondents. I want to see how much it is. Now, this was my movement around the 1 month. You see, I spend my time in Orlando all the time. Well, it makes sense because it's where UCF is. I went to the beach. I went to the airport. I went to a Costco. You can see exactly where I am. I went to Tampa, some stations. This is the GPS data. iPhone significant location, on the other hand, it doesn't give you detailed information. On Google Maps data, it gives you exact coordinates, GPS coordinate where you are, but on iPhone, you don't. iPhone only give you something like this. It's gonna give you a circle. Okay, you were here between this and that. You were at this location between this, on what day, between what time. That's the only thing you get. And you cannot export the data. In the past, you can, but no, it's no longer available since the iPhone updates about 6-7 years ago. You can no longer do that. So this is, one location. This dots are GPS dots. The circle is iPhone data. The iPhone tells me, okay, I spend my time here between what time to what time on what day. That's about it. So what I did is, okay, I'm going to interpolate the GPS data to each circle. I'm going to count how many data points, how many time I spend in each circle, and compare it with iPhone data. Makes sense. I want to see if iPhone actually captured the time I spend at each location. Now, what this means is, okay, I'm going to give you like 16 different locations. In that 1 month, I visited 25 locations in 8 cities. So iPhone actually captured 16 of them. So on a first glance, wait a second, it's not that good, but it's actually pretty good because these 60 locations account for 93% of the entire month I spend my time with. In the remaining 9 locations, 4 of them is like gas station, the pickup, drop off, and just drive by, so it's not that important. 4 locations I only visited once. That restaurant. And 1 location did not record it because it's non-compliance. What happened is at midnight, I just had a baby and the baby pooped. We ran out of diaper. And if you are a parent, this is an emergency situation, right? So I have to run to the nearest Walmart, 24-hour Walmart to get some diaper. I was in a rush, so I actually didn't carry a GPS tracker with me. Now that one is on me. But the remaining portion, what you see is that the 4 location only stated very briefly. It's not that important. 4 location only visited once. It's not shown there. So a significant location is the location where you visit a lot. So only once, maybe not that important. But nonetheless, 16 location, 93% of the time, decent, right? Now, this is the time estimate in minutes. In minutes level, this is from GPS, this is from iPhone signature location. You see 2 locations I spend most of the time. Of course, this is my home and work location. You see work, you see very clearly. And 66 times spent home, 24% time as I work. So the whole idea is, if you look at this, it's quite close. If you actually plot it, to a scatter plot, you see this is the daily time at these different locations. You see the R-square is 0.99. It's very, very good. The whole idea is, look, iPhone signal location captured my whereabouts in a month, down to minutes level, like very accurate at different locations. If we look at the time I spent, at my home and my work, you see, this, this is home time. This is GPS home time, iPhone work time, GPS work time. You see, they're really tracking location all the time. It's pretty accurate, especially at home. Work, you see some deviations, and just partially you can't blame on iPhone. Partially it's because I move around at UCF a lot. I go to a restaurant, and move to different buildings, and that you cannot if you look at the raw GPS data, you can see the GPS has a lot of drift. So the difference partially is because of GPS issues, but the thing is that the whole idea is pretty accurate. So iPhone actually track my location data pretty accurate on daily basis. And if you look at the survey, so we're talking about 74% of iPhone users actually have iPhone signal location. 74%. If you use iPhone, highly likely you would have iPhone signal location. Now, if we go back to here, is that is iPhone any good? iPhone data any good? It's pretty accurate. It's pretty complete. Historical availability and public historical availability, and also right here, population coverage relatively good. Population historical availability, we don't know. That's a problem. So how many, how far back iPhone signal location goes, no one knows, because no one have done this before. Only Apple knows, but we probably need some bigger study to understand how far back the iPhone signal location goes. Now, the one thing is easy to access, not really, because back to 7 years ago, yeah, if you use iTunes, say you back up your iPhone, there are some forensic software that can be used to extract location data from there. But Apple significantly enhanced the privacy settings. Now it's fairly difficult to extract iPhone data from your phone, because they don't give you the data anymore. It's there, but you cannot extract it. Even nowadays, you have to have a Mac and go through several complete steps, sign in, and to be able to access the data. So iPhone data is pretty hard to access. So just to summarize, Google Maps and iPhone data, they're relatively easy to access, pretty accurate to a degree, and pretty complete. It captured most of the most important locations. Considerable amount of availability among smartphone users. So again, Google Maps, we're talking about 64% up to. iPhone, we're talking about 74% iPhone users, which is about half of the population, right? The considerable population coverage. Historical availability, well, Google Maps may go back to over 7 years, but iPhone, who knows? And another thing is public acceptability. Is the public okay with it? Because it's creepy. It's clear. It's very creepy. So we're talking about tracking someone back to several months, knowing exactly where you are. It's for good reason, because it's for health studies. We want to know if Explorer give you, some other health outcomes, right? We want to know how can we do better to reduce exposure, but still tracking individual is creepy. Is the public okay with it? Because we're mining some data that has continuous being collected in the background. Many don't even know they existed. So as a matter of fact, when I do the survey, so I got some pretty angry responses from some individuals. So it tells you how sensitive this thing is. But this is a tremendously useful information in there. It's right there. How can we make use it? Right? They have a great potential. How can we use it? How can we mine it? How can we make the public acceptable? How can we better protect the privacy while make use of information? We don't know, because it's largely unanswered question open over there. Okay, now this is the first portion of my research agenda, which is individual location. So again, to get air pollution health studies better, to get exposure and to better investigate if exposure give you health outcomes, how to quantify the impact, how to better reduce it, we need to know exposure. To know exposure, we need to know human location, we need to know concentration distribution. Human location, we can mine it from different location data sets, and which is largely unexplored and a kind of sensitive topic, right? I think you can agree with me on that one. The second portion is pollution concentration. If you look at this number, you see the concentration changes substantially, spatially, right? How can we, if we know, let's see, if we know this individual's exact location in the past 10 months, we still need to know the concentration fields, right? But then the problem is, how can we do that? Concentration change all the time. Now, if you look at, for example, the concentration data in Central Florida, there are only 4 points regulatory stations in Orlando area. But of course, the concentration changes so drastically, in this area. So only 4 points is just not enough. Yes, they will have some other thing like satellite, but satellite have other issues, right? Like say it's the resolution. Let's say that if you have a cloud cover, it's gone. You don't have the data anymore, right? So there are so many issues. So So my approach to get a better spatial distribution concentration is using low-cost sensor network. So partially was motivated by this, but lack of measurement. This is regulatory station, only 4 stations here is just not enough. So what if we can just deploy much more than that? It's also partially motivated by more things. For example, environmental justice and cybersecurity issues. Now, this may be kind of nowhere, but the idea is like, okay, if you look at this, 4 locations, well, if you look at downtown, of course, you expect higher concentration in downtown, but many people actually live in downtown area are poor. And these are the people that actually impact the most by pollution. And as a matter of fact, in the Griffin Park neighborhood in Orlando, this is downtown Orlando, there have been reports saying they expose the highest concentration of pollution, and there's just nothing in there, no measurement at all in there, because it's expensive setup one in there. So another thing we want to introduce is actually cybersecurity. So for this regulatory station, they are very well protected. But for low cost, I think everybody knows low cost sensor right now. It's so popular. It's pretty cheap. You can install it anywhere. But the problem is it's not protected. Why? Because anyone can hack in there. This is one of our team. So we hijacked one of the biggest sensor network in the United States. This is the data we're manipulating. We are sending fake data to the server. So you can see we manipulate that to 0 and 151. So which means is look, cybersecurity is a concern. Some people may like, wait a second, why do I care? Because but what's the hacker gonna get out here from there? Actually, if you talk with the different entities, you know that this is a concern, because to the government, manipulating data can cause a panic. They don't want that. For the companies, manipulate, you can infer a bunch of different activities from measurement data. But one example would be that, okay, by looking at the concentration change, you can figure out the manufacturing schedule. This is a real concern from real customers, actually. You can figure out how much is being delivered and what time is being delivered. This information are commercially important. So now that's why we create this thing called Smart and Trustworthy Air Quality Network, we call STAIR in Orlando. What we want to do is we want to secure, trustworthy, reliable air quality network. So we want to build for particles, because there are 4 stations in the Central Florida region, but we want up to 100. So it gives us a wide coverage, so we can measure high density concentration distributions. We want to do a bunch of other things, like remote calibration, malfunction detection, and cybersecurity, and machine learning stuff, fancy stuff. But the most important thing is we want to have a network that gives us very highly spatially detailed information on concentrations. So, and we also want to use this as a tool. So we are playing the middleman between the city and the community being in fact affected. We want to basically to facilitate communication, use this network as a tool. So if the community is not happy, we want to know why. Why not you're happy? Can the government do better? So if you don't trust government, fine, but we are the middleman, right? We're gonna help you communicate with the government. How can the government do better to serve you, the community being impacted? So that's part of the project. We want to be able to enhance the trust in governance. And this is our final hardware design. We designed almost everything from ground up. So of course it's solar powered, because it gives us more control over where we can install it. Where even say you do not have any power outlet, is fine. You can use solar panel. This is our battery bank. This battery bank is 50 watt-hour. It's we designed our own solar charge controller. We designed our own battery management system. So this give us a very deep control. We are in charge of every single parameter on every single chip. So this way, because it's part of it for cybersecurity, we control everything. And we have a main board. So you can tell this is the main board. You can tell that something is not soldered. It's because it's COVID. We manufactured this during COVID, and we all know what happened during COVID. Chip shortage. It's extremely difficult to get anything manufactured in COVID. We design our own board, and this is a cell phone module. It's a narrowband IoT. If you're not familiar with, basically it's a very slow cell phone module. It's very slow, but good enough for us, and it's low power consumption. That's why I call it narrowband. The cell phone communication, we have CO2 sensor. We have 3 particle low cost sensor here. We have handmade solar panel support. Also have we design our own the mount support. So everything is neatly packed into one small box, except solar panel, of course. So what we do is we want to design this as an interdisciplinary network, not only for air pollution, but also for computer science, for security, and also for social science and a bunch of different fields. So that's the reason we design from the ground up. So we custom designed based on the SAMA 11 microcontroller. I'm going to rush through this because it's but just so you know, what I'm trying to say is we put a lot of thought in there. We do hardware encryption. We put a lot of 6 ports. You can mix and match different sensors if you want. If it's not good for you, sure, we have expansion chip here right here. You can basically plug more things if you want. Communication module is swappable. You can choose the Wi-Fi, a bunch of different things. We have a power outlet. If you want to hook up something that sensor that need a little pump, you can do that. Micro SD card, and you can power not only from solar panel but also from a regular household, things like this. So this is our chart. This is our web interface. You can tell that we have. Okay, thank you for the reminding. So we have. We can see in real time. This is midnight, so that's why the solar panel is not getting any power. But we can see the voltage battery, how many the wattage of battery, the battery temperature is monitored. So we build many protection in there. That's the idea. So we can see in real time what's a reading from different things. So and we also make this smart, so it can reduce the change sampling rate based on battery percentage. If we do not have enough battery, put into sleep, so it doesn't conserve battery. When it have enough power, it comes back again, comes back to life. So right now we have 47 installed. Actually, we're just more on the way. So what we did, we go to each owner's location. We ask them where to install it. We're gonna find a place where it's open. So this was on a fence. This was the church. So we install our own poles if needed. It's hard to read the pole. So we install it on the top. And if you have a location that's really bad solar power, we have a solar panel up to like 50 watt. We can install different size of solar panels. So we try to accommodate the homeowners request. So that but it means it's slow because it's a lot of work. So. And we're also collaborating with stakeholders. We contact each commissioner's office. We talk with them before even we go in, so we know that we're doing this. So every commissioner know what we're doing. We have a team at City of Orlando overseeing everything. We update them along the way. We all work with the protection divisions. So we also have a quite a broad community outreach, agenda. So we talk with different homeowner associations, or we talk with different, for example, League of Women Voters, different church religious organizations. We work with nonprofits such as National Coalition of 100 Black Women, Mom for Clean Air, a bunch of different things. We also work with the media outlets. We send out newsletter, mailing lists. We have yard signs available. So we try to make this intensive communication with different communities. We also provide community grants. So let's see, we identify the hotspot. We will give the community like up to like over $10,000, so they can they talk with the city. They can do whatever they want with the money. It's their money. It's a community grant to help with reducing the pollution. So finally, right now it's unfortunately early this year, what we noticed that is our battery bank, which 50 watt hour is not good enough. When we design this, we test it. It's good enough for 2 days. Let's see, 2 days complete darkness is fine, still running. But unfortunately, we learned Florida can have more than 4 days of continuously cloudy cover. that can be a problem. So we switch to a commercial battery module, which 128 watt-hour capacity is much bigger, much bigger battery. So we are planning to open the data to participants, and we also have a mobile lab, which is custom made for air pollution monitoring. So you can see the sampling head over there. You have another sampling head here. So we can. It has a massive solar battery, battery back in there. It can about 12,000 watt-hour. So which means you can power AC, which is AC air conditioning. You can power AC and a bunch of other things simultaneously for comfortable extended time. We can measure anything we want in anywhere. That's the idea. And as long as we can tow it there, of course. We also have a 1,500 watt of solar panel portable. So if needed, we can just hook up solar panel to the battery, so we can charge it and run it at the same time. So we're working on this. We're gonna do a lot of field work to measure pollution concentration in the entire Orlando area. So this is a shared mobile app. So by shared, I mean that if we do welcome collaborations. If you think this, if it's useful for you, if you want to use it, let me know. We are more than happy to collaborate with you on this one. So it has we put a lot of thought into the mobile lab. So you can mount equipment on top, inside, unattended, bunch of different things. So back to, I want to wrap up because since we're running out of time. So what I'm interested in air pollution. So, and exposure is the center part of air pollution studies, because we want to know if exposure gives you certain health outcomes, if how big the outcome is, and how can we reduce the bad health outcomes, right? And to do everything of that, exposure, that's the most important. Exposure occurs when you have human and pollution together. Two things: human move all the time, we want to do it better. Concentration change all the time, we want to do it better. So we can do better exposure to better serve air pollution health studies, right? Human moves all the time. How can we do that? Especially the movement already occurred in the past. We can mine cell phone data. We have 3 examples: call data record, Google Maps data, iPhone data. We can mine this data. There are tremendous amount of information in there that can be mined. But then it's no one, the study on this along this field has been quite rare. It's quite limited. So there are a lot of unknown in this area, and quite sensitive too. It pokes people's nerves, makes sense. And when it comes to pollution concentration, we want to get a better pollution field, local sensors, we can use that. It's not accurate, but we can have many, we can play different tricks to improve the quality. The whole idea is we want to use this to give us a big picture, like the detailed information on pollution concentration change spatially. So we can combine these 2 information together and give us better estimate of exposures for air pollution health studies. So we can know, what health outcome it causes, how bad it is, and how can we do better to serve the population to reduce the impacts. So yeah, that's all I have. So I'll be happy to answer any questions.
Great. Thank you, Haofei, for